Okay, just checking. Are we live from the chat? Are we online and good and alive? Can you guys hear me? Am I audible? From your own screens. Feel free to give an indication. The other day I had a stream and there was a few bugs. So I'm hoping to sort of mitigate those bugs. Um, there. Okay, guys. Are we online? Can you guys hear me? Am I audible? Hopefully this mic is working out pretty well. Awesome. Okay, great. Welcome everyone to the live stream for linear algebra. I can see that linear algebra is not exactly the easiest subject for one to learn, but nevertheless, of course, there are some interesting ideas in this subject. All right, awesome. We are audible, we are live, and we're good to go. So feel free to field your questions. Yeah, feel free to raise your questions in the chat. It could be ranging from general questions to more specific questions. If it's questions pertaining the exam, unfortunately, I do not know much about it. All I know is that you can use MATLAB in your exam, so that kind of helps a lot of course, when doing Gaussian elimination, because who likes to do Gaussian elimination by hand, am I right? Yeah, okay, so without further ado, I didn't really plan any particular discussion necessarily for today. But I guess maybe to warm things up, just to recall, as you guys are very well aware of, I always highly strongly recommend matrix multiplication from the perspective of a recipe, right? I know I've been drilling this down for like the past few weeks now during the lessons, but it's best repeating, because instead of thinking of this as a really massive calculation, one could interpret this as simply sort of creating a dish where you use C1 amount of ingredients of the form 1, 2, 3. So you can think of it this way. And C2 amounts of 4, 5, 6. And finally, of course, you have C3 amounts of 7, 8, 9. Oops. So this idea is surprisingly versatile. It actually explains many ideas like linear independence, linear spans, subspaces, null spaces, row spaces, column spaces, all that good stuff. It's really quite useful. And feel free if you want me to elaborate on that idea. All right. Feel free to fill your questions in the chat, and yeah. Either you can do that, or you can just enjoy the music to study some linear algebra. All that's well and good, and yeah, feel free to take it away. I have no idea who's online now, but since we are all online, that's good. Whoever is online, I have no idea. I'm not really tracking the particular statistics and whatnot, but yep. Okay, so off to you guys. Okay, At the moment, I don't see any questions. I do have some ideas to sort of talk about at the back of my mind, just so to keep some of you entertained if you're curious. Okay, matrix is basically a recipe to transform. Determinant represents the area stretched by the matrix. If the determinant is non-zero, the area can be inverse. Yeah, exactly. That's exactly the idea. So the determinant does, in some sense, measure how much the space gets stretched. Okay, how do you determine the relationship between eigenvectors and eigenvalues? This is essentially the most recent idea that we've been talking about. And so, roughly speaking, here's how I sort of explain these two ideas. So roughly speaking, even though matrix multiplication is made easy using the recipes idea, it still might be a little bit challenging, right? Wouldn't it be nice if we could find a vector such that matrix multiplication turns out to be scalar multiplication? Could this somehow, in some bizarre world, be possible? Now, if that is possible, we would say that V is an eigenvector. So in fact, we can define an eigenvector. So we'll let V be a non-zero vector. We say that V is an eigenvector of A precisely when you can find some real number lambda with the property that matrix multiplication turns out to be scalar multiplication. In this situation, we call this guy an eigenvalue. And the thing about eigenvalues is that eigenvalues aren't the key player in this discussion. The real star of the show actually is the eigenvectors, because those are what helps us have ease of calculations from matrix multiplication to scalar multiplication. So that's the core relationship between an eigenvector and an eigenvalue. The eigenvalue is basically how much you're scaling a vector by. For this particular vector, because not every vector has this special property. Only a few vectors out there have. Yeah. So that's essentially the idea of that. Of course, there are a few algorithms you can use to calculate eigenvalues and eigenvectors, but those are sort of consequences of this consequences of this fundamental definition of the two ideas. So maybe I think we can do a quick example over here. For example, for this guy, a natural question to ask is what exactly are the eigenvectors of this matrix? It's a really natural question to ask. So in other words, is it possible to find vectors, a vector v and a scalar lambda, such that this is true? Well, to sort of simplify things, let's call this A. And what we're trying to find, our goal, is to find a non-zero vector v such that AV equals to lambda v. Now, with some thought, you could rewrite this as the matrix equation lambda I minus A v equals to 0. And what that means is we are looking for a non-zero vector that satisfies this matrix equation. And it's not just any matrix equation, it's a homogeneous equation. That tells us that there's only one instance in which this is possible, because when we have a homogeneous equation with non-trivial solutions, we must have that the determinant of lambda I minus A is 0. Or I guess more generally, or more fundamentally, we need to have that lambda I minus A is non-singular invertible. Non-invertible. Sorry. It has to be singular. There we go. Oops. So you can use this algorithm to obtain the eigenvalue and use the eigenvalue to obtain your eigenvector. Okay, I do have some ideas I was thinking about throughout tonight, and maybe perhaps sort of satisfy the curiosity from some of you guys as to why we give some ideas certain names. So for example, we know, speaking on the topic of systems of equations, we know that, or at least we are taught or sort of aware that we call this guy, we call the vectors, okay, that satisfy this equation. So let's call it this way. We call the set of vectors that satisfy the homogeneous equation a solution space. And in the context of linear algebra, space usually corresponds to vector spaces. So what does a row space and column space actually mean for the matrix? Are they just the basis, and what's the significance? That's a really good question. And it's actually linked to this idea of the solution space. In fact, we can look at that first because we're dealing with the matrix A. So it's interesting because the column space is something that you guys are already familiar with. Okay, so what do I mean? We'll let A be the matrix A1, A2, and A3. Of course, you can generalize accordingly, right? You can generalize. So what is the column space of A? And I'm gonna use this notation. This is my personal notation for the column space of A, right? Math people are really lazy. It's essentially the span of the columns of A. But interestingly enough, we can actually interpret the column space of A in a very, very different manner. Okay, so how do we do that? Well, it turns out that what are if we were to consider all the different possible inputs, so say we'll let V be an input vector, and we want to transform it using the transformation A. What's the outcome, right? What's the outcome? Well, the outcome of AV is going to be A1, A2, A3, and let's say V1, V2, and V3 is given by these coordinates. Let's call it C1, C2, and C3. Using the recipes idea, when we do the sort of C1 amount of A1s and C2 amount of A2s and C3 amounts of A3s, we're going to get this quantity, C1A1 plus C2A2 plus C3A3, right? So in other words, A of this vector is given by this linear combination. So what are we doing here? If we were to collect all of these possible, right? If we were to collect all the possible outputs given any recipe you plug in, oops, right? What do we obtain? Well, by definition, A of C1, C2, C3 is basically C1A1 plus C2A2 plus C3A3. Oops. I'm just going to abbreviate by saying Ci and R. But this is nothing more than the definition. This is actually the definition of the span of the columns. So it turns out you actually get this really amazing property that the column space of A can be thought of as essentially the collection of all the outputs under the transformation A. So that's a really useful idea. Now the column space itself, that's the column space. The row space has its purpose as well, and it's linked to this notion called the null space. So I mean, since we're on the topic of column space, row space, and null space, let's look at all of them together. Some of you also know that this is not just called the solution space, this is also called the null space of A. Again, that's my notation for null space of A. And the idea is that, why do we call it a space? It's because it should be a vector space, right? So roughly speaking, the null space tells you all of the vectors that get killed by A. Roughly speaking, right? That's what it sort of tells you. You plug in the vector into the matrix A, you get a zero output, right? And it turns out that the row and null space are essentially perpendicular to each other. Alright, so the technical term is this idea of an orthogonal complement. And you can actually work it out through dot products. But that's roughly speaking the connection between row space and column space, row space and null space. In some sense, it's sort of all of the vectors that are perpendicular to the null space. So there are significances. I wouldn't say it's very prominent at the year one linear algebra level, but definitely as you progress further and you do use the more interesting sort of machinery, there are some really useful components from it. Yeah. So just to sort of show everyone why this is called a solution space. Okay. So why do we call this a solution space? Well, because roughly speaking, it should satisfy the vector space properties. And so of course people are wondering why on earth is a vector space, right? Well, basically we need to make sure that the combinations are pretty nice. What do I mean by nice? So we need to make sure that this guy satisfies three criterion. We're going to call this S. We'll call this V. Let's call this V. We need to show that the zero vector lies inside V. That if we take two items in V, the output remains in V. And finally, if we take a vector in V and scale it up, then scaling the vector should lie inside V as well. Right? So let's take a look at why this is the case. Let's check. If we plug in 0, right, as an input, what's the output of A multiplied by 0? Well, A multiplied by 0 is going to be 0. But that means that 0 actually satisfies this equation. So therefore, we can conclude that 0 lies inside the vector space. Next up, what does this mean? Well, since U and V lie inside the vector space, we know that AU plus AU equals to 0 and AV equals to 0. So that raises the question, if we were to plug in U plus V, would this equal to 0 or not? Well, we know that matrix multiplication, you can sort of do a distributivity there, but AU is 0 and AV is 0. Right? So therefore, these two properties work. And finally, since U lies inside V, this means that AU equals to 0. So the question now is, if you are plugging CU, does this equals to 0? Well, if we know that using linear algebra, well, because A is a linear transformation, we can pull the C out, but AU is 0. Therefore, if we plug in CU, we do get 0 as well. And that's why we call it the null space, because it really does form a very nice vector space for our purposes. Right, so there is a very close connection between the row space, column space, and the null space. Yeah. We've got a question: if an n by n matrix has distinct eigenvalues, if an n by n matrix has distinct eigenvalues, are the eigenvectors limited to n, or are there infinitely many eigenvectors? That's a really good question. Okay, so it depends on what we mean by infinitely many, right? So in a sense, strictly speaking, if we were to look at the raw information, the answer is, well, yes, because, well, let's let V be an eigenvector of A with eigenvalue lambda. Okay, so what do we mean by more than n eigenvectors? So let's take a look. Well, this means that A V equals to lambda V. Right, that means that. So what about if I were to choose your favorite real number, fix your favorite real number. Aha, exactly, we've got closure properties in mind. Well, if you have a real number, what would be A of CV? Well, that would simply be C times AV. Right? That would be C times AV. But what's AV again? AV is, since V is an eigenvector, is lambda of V, which means that lambda, this equals to lambda of CV, because you can swap the constants. But this tells us, what does this tell us? This tells us that, wait a minute, matrix multiplication applied to CV, it corresponds to scalar multiplication. So therefore, CV is an eigenvector as well. But C is any real number you wish. So that actually gives us infinitely many eigenvectors. Now that being said, I think I know what we're referring to, more than n eigenvectors. I think to be more precise, we should say that a matrix A has at most n linearly independent eigenvectors, right? So the set of eigenvectors that A can have, the set of linearly independent eigenvectors that A can have, has at most is at most n. So if you were to ever choose a bunch of eigenvectors that are linearly independent, the largest that this collection of eigenvectors can be, the largest size, is n. So we'll say this: let S equals to v1 dot 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 vk be linearly independent eigenvectors of A, then we know that k must be at most n. Okay, so choose any set you want. If you want them to be linearly independent, you can get at most n of these eigenvectors. Yeah. In fact, if A has n linearly independent eigenvectors, we actually say that A is diagonalizable, which is a really, really nice property. Exactly, if you have more than n, you definitely have redundant vectors, it cannot be linearly independent anymore. Yeah. Exactly. That's awesome. Yeah. I mean, I guess I'm just want to put this over here. I guess there are some interesting sort of little exercises to try if you're curious. Here's an exercise. You can try to show that V is an eigenvector of A to the power of your favorite natural number with eigenvalue lambda to the k. You can try that out. It's not too challenging of an exercise there. Right? You can actually try that question out. Right? Let me know if you want me to do a quick proof of why this is the case. There are actually a few really nice eigenvector properties over here. Thankfully, you guys don't have to marry eigenvector with orthogonality. That's a new layer of complications which students in the other linear algebra class have to do with. That gets fun. That gets fun. Alright, there's actually a really interesting result in the linear algebra. Some of you know about this. I think it's been mentioned before in the lectures sometimes. Is this called the rank nullity theorem? It sort of tells you how big your column space can be. It turns out that your column space and your null space, you put them together, it sort of tells you the largest possible sizes you can get. So there's that. Maybe a little out of scope, but is the C1 of of SDE, definitely real numbers. I think within the context that we're working in, the answer is yes, because we are trying to find, we're working what we call a vector space over the real numbers. I think there are ways to sort of extend this idea. I think there are ways to extend it because there is a very useful notion in math called vector spaces over complex numbers. Complex numbers has really nice properties. You can go check it out in Linear Algebra 2, MA 2101. Really fun stuff there. I think it's possible, but at least for now, we are working within vector spaces over real numbers, which means that the recipes you're working with are real number recipes. Yep. Yeah, so there's this rank nullity theorem, really nice idea, really quick proof even. So you have a matrix A, right? Let's just say you have, the size is not really relevant, but you have, say, n columns, right? You can perform Gaussian elimination on it. You can perform your Gaussian elimination. You're going to get some number of rows, some number of pivot columns, non-pivot columns, all that good stuff. Let's just say we get this instance. Right, so these guys are pivot columns and these guys are non-pivot columns. So, well, we have a certain number of pivot columns and a certain number of non-pivot columns. So the rank nullity theorem tells us that the rank of the matrix plus the nullity of the matrix should equal something. This, roughly speaking, tells us the dimension of the column space of A, and this tells us the dimension of the null space of A. So the dimension of the column space of A, well, I probably should have used different colors to denote that. Let me try that again. The column space is given by the number of non-pivot columns. That's a really interesting fact there. Right, so this is equals to the number of the number of pivot columns. And then the null space, or rather the null space, the dimension of the null space is given by the number of non-pivot columns. But this just gives us the total number of columns. And this is precisely the rank nullity theorem. It helps us connect these ideas together. Yeah. So it's really fun, really interesting things there. Has its own applications, has some really weird challenging questions out there. I don't think these are the one, in the linear algebra course. So there'll be the other one. This one, there's always these what I call black magic questions, where these are questions designed to sort of weed out the those who know what they're doing. And it's like, it tends to be the really tough questions. I remember when I did linear algebra, I couldn't do the black magic questions as an undergraduate. But of course later on, when you appreciate a bit more math, then it's like, okay, it's starting to make a bit more sense. Yeah, so I do have some very interesting questions. I actually did like a whole, like how many hours? Like I think it was might have been like 4 hours or something like that. I'm not too sure, of difficult linear algebra questions. It's somewhere on the live stream. You can go check that out if you're that interested. If you're not interested, no worry, no sweat. Yeah. Feel free to fill those quiz questions also. I mean, of course, you have to sort of describe the question in detail, because I'm not too sure how to what do you call that? I don't really have access to the answers, all the questions, or I think I do, but I'm not gonna bother with it. Feel free to raise those, because those really appeal to the conceptual complexity of the subject. Yeah. Okay, looks like we're not the number of questions have dwindled, so we might have an early night tonight. We might call it early today. Any burning questions from the chat for the rest of the evening? Yeah. Okay. I guess. Oh, is there? Do we have something here? Tutorial questions. Yeah, sure. Let's talk about some tutorial questions. Let's go for it. Yeah. Let's talk about some tutorial questions, which might be a little more challenging, or a little bit more complicated. Yeah, we can talk about the tutorial stuff. Yeah. If you guys want a quick explanation as to why stacking works, I did do a little bit of a housekeeping notes on why that works. But if you want an explanation of why it works here, it makes sense. Again, it actually goes back fundamentally to the recipes idea. So that's pretty cool. Okay, so we have a question here. Okay, so this will be interesting. We have this question over here. We need to find a basis for the eigenspaces of A with the relevant eigenvalue. So we're given some transformations. Okay, we're given some transformations. Okay, I don't know if I can actually answer graded work online here, but I will sort of at least highlight some key ideas which are worth discussing, right? So I won't really go into the full solutions, but I will highlight some ideas which might be useful. So we'll do that. So here are some here are the given information, and we're looking for the different eigenvalues and eigen spaces associated. We're going to stacking in a moment. Stacking is pretty cool. Yeah, okay, we're going to stacking. So we want to find the eigenvalues and eigen spaces. So the first thing I notice is the fact that right away these two give me some interesting information, because these two sort of components tell me that A of 0, 1, 0 is equals to the 0, 0 vector, which tells me that 0 is an eigenvector. 0, 1, 0 is an eigenvector with eigenvalue 0. And the second piece of information also tells me, right, that if you plug in 0, 0, 1, you will get -1 of 0, 0, 1. Some people were asking me like, wait a minute, is that a simple is it that simple of a solution? Well, the answer is, well, yes, right? This is the definition of eigenvectors and eigenvalues, so this is entirely legitimate. But of course, the real question that's worth considering is precisely this last piece of information right here. All right, so we'll talk about the legitimacy of stacking in a moment. But it turns out that you could actually, in some sense, obtain the matrix A to be, you could essentially stack the inputs and the outputs together. Stacking sort of is the generalized version of the fundamental idea. So what do I mean? So when you stack, you put in the inputs here, you put the outputs here, okay, and the inputs are going to be, these are the inputs. Oops, sorry. These are the inputs. Make sure that they are linearly independent because you want to do matrix inversing in a moment. And then you want to plug in the output in the corresponding column. Of course, the more interesting element is why on earth does this work, right? So there's that. Now, the next input we'll put here and the output we'll put there. And finally, the last input and output pair, I'm going to put it here as well. 0, 0, 1, 0, 0, minus 1. So it turns out that A is the eigenvalue -1. Oh yeah, it's -1. That's thanks for the verification there. It turns out that, wait a minute, this is identity matrix, so actually we obtain just the matrix itself. This is why the basis vectors, in a sense, is a sort of consequence of stacking, but I'll briefly explain how the reverse actually happens. Okay, so we have A, and what we need to do is to calculate the eigenvalues of A. And you might be wondering if we need to run through a very complicated algorithm. Interestingly enough, the answer here is no, because we do get a triangular matrix. This is actually a lower triangular matrix, which tells us that the eigenvalues are just these guys. The eigenvalues are the A has eigenvalues -1, 0, -1. All right. You've asked a really good question on the PD thing. I want to get there after this question because it's really interesting. And it's actually linked to stacking. Surprise, surprise. So we have -1 as the eigenvalue and 0 as the as an eigenvalue as well. At this moment, I'm tempted to just try to calculate the eigenvectors, but I'm not too sure. I think if I'm right, if you run through the algorithm, if I recall correctly, please correct me if I'm wrong, but I think the only eigenvectors you get, okay, I'm not too sure, but I am going to conjecture because I briefly saw it. I think these are the only two eigenvectors you will get, to my understanding. And so what happens here is that you have the eigenspace associated with the 0 vector, the 0 eigenvalue, sorry, with basis 0, 1, 0, and -1 equals to span of 0, 0, 1. Help me check if this is really the case, but if I recall correctly, this is probably the solution. Now, the thing about PDP inverse is that there's something really interesting that happens. So, okay, so sometimes we will get, as I mentioned before, A has n linearly independent eigenvectors. For a basic question, recipe idea, the second matrix is this guy multiplying by matrix earlier. Okay, we will come to that. That's a good question. Okay. Let's talk about the PDP inverse. So we say that A has linearly independent eigenvectors, or rather we say that A is diagonalizable precisely when it has n linearly independent eigenvectors. Okay, 3x2 matrix. We'll get to that. Actually, we can really modify the recipe idea. Essentially, you're creating a bunch of dishes. Okay, you can think about that. A is diagonalizable precisely when you can find a matrix, two matrices, P and D. P is invertible. D is a diagonal matrix with the property that P inverse A, P equals to D. So here's the question: what on earth has this notion of being diagonalizable has got anything to do with the linearly independent eigenvector situation? Now here's where stacking comes into the mix. It's really cool. So well, if A has n linearly independent eigenvectors, we'll let them be denoted by v1, v2, all the way to vn. Okay, and let's suppose they have eigenvalues lambda 1, lambda 2, all the way to lambda n. Right, the lambdas may repeat. We have no idea. It's fine. But the point here is that A V1 equals to lambda V1 and A V2 equals to lambda V2, so on and so forth. A Vn equals to lambda Vn. Using stacking, we can stack the inputs together. Let me write it this way. We can stack the inputs together and we can stack the outputs together, right? But what that means is we can stack the input V1 with the output lambda V1, V2 with the output lambda 2 V2, and Vn with the output lambda n Vn. Okay, this is really, really cool. Oops. Okay. So this turns out, because these guys are linearly independent, this whole matrix is invertible. In fact, this is precisely the invertible matrix P. Right? This is actually the invertible matrix P. On the other hand, if you were to sort of do a bit of matrix multiplication, you sort of undo the recipes idea, you're actually going to get V1, V2, Vn, and a diagonal matrix. So it turns out that the left side, you get A, V1, V2, Vn, and on the right side, you get the same matrix multiplied by the diagonal matrix. So if you let this be your P, and you let this last matrix, this diagonal matrix here be your D, check this out. You get AP equals to PD, which simply means that P inverse AP equals to D. So that's actually the connection between the eigenvectors definition and the fact that you can find the PD matrices associated with a diagonal matrix, a diagonalizable matrix A. Right, and we'll see some applications of that when in a few days ahead when we look at taking powers of matrices. So that's actually the sort of why this appears. It actually comes from the definition of having linearly independent eigenvectors. So really, the eigenvectors play a crucial role in this whole discussion. Now, over here, a really, really interesting idea here. Let's look at the recipes idea, right? So let's take a look. So let's say we want to take the matrix 1, 4, 7, 2, 5, 8, 3, 6, 9, and we want to multiply with the matrix C1, C4, okay, there we go, C2, C3, C5, C6, right? So sort of, how do we sort of apply the sort of the recipes idea to matrix multiplication? Well, most of the times, so far we've discussed, we've been working with matrices of the form we multiply by a vector. But now we want to ask the question of multiplying by a matrix, right? So the key trick here is to treat these guys as two different dishes. These are two different recipes for two different dishes. So what do I mean? Well, how many dishes are you cooking? You're cooking two dishes, right? So we're gonna prepare two dishes for ourselves here. In each dish, what recipe are we using? Well, the first dish, right? The first dish can be thought of as C1 ingredients of the first, C1 units of the first ingredient, C2 units of the second ingredient, and C3 units of the third ingredient. So actually, for the first dish, we're going to get this combination. That's our first dish, right? That's our first dish. All right. What about the second dish? Well, the second dish will be using the second recipe. So this is where we use the first recipe. Oops. We used this recipe just now. Now we'll use the second recipe. All right. The second recipe tells us we want C4 units of the first ingredient, C5 units of the second ingredient, and C6 units of the last ingredient. All right. So there are some implications from this way of thinking, and I think we actually have the idea below us right there. But let me write this down properly. So here's the interesting thing. When you do matrix multiplication, essentially you can sort of multiply the matrix into the quote-unquote recipe matrix, right? Because you're sort of applying this recipe onto these ingredients. So this is the dish that you obtain, and you know, with this recipe on these ingredients, you're gonna get this dish. So it's really useful idea. Can a matrix always be diagonalized by Gaussian elimination if it's diagonalizable? I think we had this discussion. Some of us had this discussion where how is Gaussian elimination related to diagonalizability? In general, they are not related at all. Yeah, in general, these two ideas are completely separate. And the fundamental issue is roughly this, right? Don't even talk about diagonalization. Let's just first talk about A. When you apply a rule, a sort of one of the operations, a rule operations from Gaussian elimination, you sort of change the matrix. But if you change the matrix, you're essentially changing the transformation. And once you change the transformation, all bets are off as to whether or not the eigenvector will remain an eigenvector in the new transformation. In other words, if V is an eigenvector here of the first matrix, it may not necessarily mean it's an eigenvector of the sort of row equivalent matrix. You might be curious to wonder if it works for column equivalent matrices. Not too sure about that, honestly. I have a hunch it works, but for row equivalent matrices, all bets are off. Yeah. So in general, diagonalization and diagonalizability and Gaussian elimination in general do not have very strong connections, especially like even invertibility and diagonalizability. I think we talked about this briefly. If you have a matrix that is singular, not singular, diagonalizable and not diagonalizable, it turns out you can find a matrix that is singular and diagonalizable, a matrix that is not singular and diagonalizable, a matrix that is singular and not diagonalizable, and a non-singular matrix that is not diagonalizable. Turns out that all four cases are possible, and there's no immediate connection between them. Yep. Okay, so I remember just now we wanted to talk about stacking a little bit. This is where you're sort of teasing the nerd in me, right? So here's the thing about stacking. It turns out that stacking is a consequence of the basic idea of a linear transformation, right? So what do I mean? So suppose give an example of the P inverse AP. Okay, let me just do this. I think there were some examples in the in our tutorial, but I'll just grab one of those examples and then we'll work from there. So we have here, okay, for C, for example, here's the matrix here, okay, and we're going to stacking in a moment because that's fun. For C, let me look at the matrix. We have this matrix. You can actually check that it has eigen vectors and eigenvalues given by, well, it has an eigen value -1 with this basis. Oops, it's the span of this basis, and the eigenvalue 1 has the span of this basis. And firstly, we observe that we do obtain 3 eigenvectors, and it turns out that we can prove it. We can actually prove this, and again, if you're curious, I can do that. That this must be linearly independent. Now what this means is that we have 3 linearly independent eigenvectors, which means that C is diagonalizable. But if it's diagonalizable, it means that there are matrices P and D such that P inverse CP must equal to D. Agree? So how do we calculate the P's? Once you have the eigenvectors, it's actually not too difficult to calculate the P's. Because all you need to do is to plug in each of these eigenvectors as columns of P. And for the diagonal matrix, you just need to plug in the corresponding eigenvectors. So what do I mean? Eigenvalues. So what do I mean? So for minus 1, 1, the eigenvalue associated to it is minus 1. So we plug in minus 1 in the corresponding entry. It has to be corresponding, all right? So that there is that restriction there. But otherwise, there's that. And then for 1, 2, 0, you can plug in the eigenvalue 1. And finally, for the eigenvector 1, 0, 2, you can plug in the eigenvector 1 as well. And that's essentially how you can calculate the P inverse AP, right? Okay. Let's do some fun stuff here. Let's talk about stacking. Stacking is really cool. So the real question, for example, if you have AU1 equals to V1, AU2 equals to V2, AU3 equals to V3, and of course you assume U1, U2, and U3 are linearly independent, then why does this work? It's interesting actually. I think we actually have the answer from just now, right? So someone asked about matrix multiplication involving these guys. Well, you can think of this as the recipe for this particular dish. This is the recipe for this particular dish. And this is the recipe for this particular dish, right? So you can think of that, right? I'm gonna just, ignore this for a moment. Based on our discussion just now, it turns out we can actually write this as AU1, AU2, AU3. Well, but we know that AU1 equals to V1, right? So it's interesting because you gave an even faster explanation as to why stacking works. It's because essentially each item here represents one dish, right? The recipes for 3 different dishes, and sort of you can sort of put them together. Here are your 3 different dishes, but these dishes are given by these quantities. So I gave a slightly more long-winded explanation involving the what you call that, involving the standard basis vectors. Yeah, but that's something. Yeah. So hopefully you can see that the linear algebra here is really less about the calculations and a lot more about different ideas. And calculations really sort of can be facilitated using technology and whatnot. But the ideas are really, really quite interesting. Yeah. That's really cool, I have to say. Yeah, the ideas for linear algebra are really, really quite cool. Yeah. Alright, anyone has any other burning questions to ask that we want to sort of get off our chest, and any curiosities you want to satisfy, any interesting ideas that you want to discover, feel free to raise them in the chat. If we don't get any questions, we'll probably log off soon. Have an early rest for everyone. Probably let's just see how many questions we have left. I think if there are no questions, I will sort of end the chat and end the stream at 11:30. Okay, so we'll keep it short and sweet today. Yeah, don't need to turn the Q&A into another tutorial session, right? With another one of group discussions and whatnot. Yeah. And of course, for anyone who is tuning in, who is not part of the module but are here because you guys like Kindiak Math, welcome here as well. Fun stuff ahead. Yeah. Some really interesting ideas. I do plan to make a video on this idea of matrix multiplication as cooking. I'm slowly sort of conceptualizing the idea and thinking of how to go about it. But that will be interesting when we get there. Yeah. If integration exists, why are we using linear algebra to solve differential equations? Well, it depends on what you mean by using linear algebra. It depends on using integration exists. So I think you are probably referring to equations that look, roughly speaking, a bit like this. And of course, I'm using the easiest one possible, right? But you're sort of looking at equation that looks like this, right? And so you're thinking, well, why not just put the x over? Sorry, why not just, sorry, this should be a y. Okay, y. Why not bring the y over, do some integration and so on and so forth? And the answer is, you're not wrong. They actually did that, did the integration. But here's the fun part. What happens when you have whole systems of differential equations, right? It turns out that you can rephrase the differential equations. So in some sense, each equation here is a differential equation, and you want to solve them all at one shot. Linear algebra provides you with really powerful tools to do so, right? I think you've already had a taste of that. I remember I had to do this in this module in NUS as well. It's called MA3220, the ordinary differential equations. Over there, you actually sort of learn you solve n by n systems of differential equations. And eigenvalues, rear the ugly heads as well, all that good stuff. Yeah, so is that. Is it one eigenvalue corresponds to only one eigenvector? Not necessarily. One eigenvector has one eigenvalue, but one eigenvalue may have multiple eigenvectors. Right. So a very sort of a classic example is actually just the example just now we gave is a good one, because this eigenvector has only one eigenvalue. Right. Every eigenvector has only one eigenvalue. However, this eigenvalue has two different eigenvectors. So it's entirely possible to have one eigenvalue, but yet multiple eigenvectors. Yeah. When I wrote this down, I think I wrote this somewhere above here. Somewhere above, I wrote something about eigenvectors and stuff. I'm not sure where I did it. There we go. Oops, I should have put lambda 1, lambda 2, and so on and so forth. I do not know whether some of the lambda i's could have repeated. I just don't know which ones. Yeah. So really the core idea of eigenvector and eigenvalues really are the eigenvectors. The eigenvalues are like sort of playing a supporting role, right? That's that. But feel free to prove this sort of claim. Feel free to prove it. If A, of course, an n by n matrix has n distinct eigenvalues, then A is diagonalizable. Check it out. It's a really cool result. You might need to prove a smaller result, which I can do if you guys want, but I'll probably leave it as an exercise. If A has eigenvectors u1, u2 with eigenvalues lambda 1, lambda 2, such that the two eigenvalues are different from each other, then this set u1, u2 must be linearly independent. I proved it sort of as a post-class discussion. I think last Tuesday. Yeah, some of your friends have those notes, so you can go and back them for that if you're curious. Yeah, but you can use this lemma to sort of prove the claim. Yeah, in fact, you can prove the lemma and then you can use the lemma to prove the claim. Yeah, so that's that. Okay, we are 1 minute left up to 11:30. If you have any burning questions, now is the time. Probably gonna close up in a minute. Yeah. Oh, and for integration, the sort of to derive the method actually does involve our integration. That's how we get the e to the kx terms. Yeah, we're actually using that. All right, it's 11:30. Thank you guys for watching this live stream. If you want to go and check out some of the other linear algebra that I've done, either I think there's a nutshell video and there's like some black magic questions, you can go and check it out on the channel. For this video, I'm gonna put an end card as some linear algebra video. So knock yourselves out.